Okay, so in the previous videos we discussed the major losses, and the major losses are delta P due to a wall friction of a long section of pipe. Now we're going to discuss minor losses. Okay, and this is a pressure drop as the flow moves through elbows, valves, reducers, expanders, etc. Okay, and so you can sort of think of this as a picture of a valve could look something like this. So you have the pipe coming in over here, some sort of structure here, and then you have the stopper for the valve right here that's connected to the handle. And then the flow goes off to the other side. And so the streamlines, as it goes through this valve, even if it's wide open, they have to go down, around, through here, turn, and then go around back down, and all sorts of stuff. And so in these valves, the flow is very, very complicated. There's a lot of viscous effects as the flow goes over and around all the obstacles, around the valve stopper itself. And so there is a significant pressure drop from the start of the valve to the end of the valve, even if they're fully widely open. And the same thing goes for an elbow. If I have an elbow, which is just a turn in the pipe, well, as the flow, say if it's perfectly laminar going in, well, as the flow goes around the elbow, the velocity profile is actually going to be kind of messed up. It's going to look something more like this, where the peak velocity is going to be closer to the outer wall, and so on this outer wall there's going to be a lot of extra viscous stress, which means there's extra wall shear stress here, which means there's extra pressure drop, and it'll take some time, and eventually the flow will become fully developed again. And while this while this messed up velocity profile is becoming fully developed again, there's a pressure drop associated with that, and that is taken into account in the entire delta P for an elbow. And so, however, these are called minor losses. Because from the point of view of a very long pipe with a huge L over D, minor losses tend to be small. Okay, and so they're called minor because if you're from the point of view of an oil pipeline, which can be many hundreds of miles in length, the flow loss through the valves and elbows and bends in the pipeline simply don't matter compared to the major losses or just the wall shear stress from the pipe itself. However, I don't like the term minor loss and major loss because it implies one is always major and one is always minor. There are some piping systems, like for practical mechanical engineering purposes, where you're dealing with hydraulic systems and things like that, where your pipelines aren't very long, and in those cases, sometimes the minor losses can be greater than the so-called major losses. So just be careful. Okay, and for minor losses, L over D does not make sense. So we use the other form where delta P is equal to a loss coefficient, a KL, times the dynamic pressure. Okay, and this here is a loss coefficient. And this is dependent on a lot of things. Okay, and so, and you can find these in tables in the book, and and so you can see table 8.2, 8.3, and 8.4 in figure 8.15 for some examples. And in general, for engineering purposes, a lot of pipe manufacturers and component manufacturers will actually give you data on the loss coefficients for their components, so you can accurately design something. Okay, and just to provide a few examples, if we have a tank and a square-edged inlet, gotta spell that right. Well, the streamlines will go down, around, and over it, and the same thing through for the bottom. And I drew that really wrong. And as the flow goes down, around, and it overshoots, there'll be a little recirculation zone in here. And this neck region here is called the vena contracta. So the vena contracta sort of reduces the actual flow area because the streamlines are going down and around, and there's no net flow going through this region here. So, and there's another vena contracta down here, so I'll just get rid of this inlet thing so I can draw the streamline. Okay, and so the area, so the actual flow area is actually this smaller area here. And so that has the effect of reducing the net flow, and it takes a lot of energy to actually run these recirculation zones. And so there's a delta P. And so for a square inlet, can't spell today, the loss coefficient KL equals 0.5. Okay, now you can decrease the loss coefficient by simply rounding this corner and making it smoother. So if we round the corner and make it smooth with some radius of curvature and some diameter d, the streamlines don't form that vena contracta, and the pressure drop is mainly due to just wall friction as the streamlines go over and turn. And so here, for these, KL is about 0.3 to 0.04. And so this is large, oops, not L over D, R over D. D, and this is small, R over D. Okay, and so here, with these ones, we have a very small radius of curvature, which means we are approaching the square corner limit. Okay, and note that the loss coefficient is not zero, even for a very large, very smooth contoured inlet, and that's simply due to the wall friction as the flow goes and turns around the long rounded sides. Okay, and also you can have cases where you have the tank, and the walls of the tank are here, and the pipe actually sticks into the tank a bit. Okay, and here the loss coefficient is actually pretty large because the streamlines have to go down, around, turn, and then go in there, and then go into the pipe. So in situations like this, the pipe sticks into the tank. The loss coefficient is about 0.5 to 1.0 depending on L, and I'll just call this L here. Okay, and so it depends on how far it sticks in. If L is 0, we approach the just square cutoff limit, and it's 0.5. If L is sticking way into the tank, then it's 1.0. Okay, and so there are all kinds of tables and charts in the book that have examples of these loss coefficients. And so now now we have went over the major losses, the minor losses. Now we got to go over like what on earth we got to go over. So why do we spend all this time? Sure, we can compute a pressure drop in the pipe, but why do we care so much about the pressure drop? So I spent all this time. How do we use delta P major and delta P minor? What do we do with this? Well, we use them in pipe flow calculations. Okay, and so here, this is viscous, so this implies we cannot use Bernoulli. Okay, so just a word of warning: if you're doing a viscous pipe flow problem and I see somebody using the Bernoulli equation, I will take off massive points, just because the Bernoulli equation is completely incorrect. Instead, you need to use the energy equation. Okay, and so we'll just consider a generic, and so we are going to derive that. So we're going to consider a generic pipe system. Okay, and it'll be a fairly simple pipe. So we'll have just a pipe, and there'll be a pump P, a turbine T, and an inlet and an outlet. Okay, and so what we're going to do is we're going to apply conservation of energy, and we'll just choose our control volume to go over the inlet, the outlet, and over the turbine and the pump. And so I'll call this section 2 and section 1. This is to be consistent with your book. And we'll have a W dot in from the pump, a W dot out from the turbine, and also we'll have a Q dot loss as heat goes out. Okay, and we're going to assume steady, incompressible flow. However, we cannot assume uniform flow on the velocity vector, okay? Because we know that whether it's turbulent or whether it's laminar, there's going to be a velocity profile, some sort of velocity profile inside of the pipe. Or if it's turbulent, it'll look something more like this, okay? And so we need to account for these velocity profiles, so we can no longer assume uniform flow. So then we got our control volume here. We use conservation of energy like we always have. We have partial t, the integral over the control volume of rho e dv, plus the surface integral of e plus p over rho v dot n hat dA, equals w dot in minus w dot out plus q dot in minus q dot out. Okay, and I'll just assume there's no heat going in. It does not matter for these types of calculations. It's steady, so this goes away. And so, and E is equal to, I'll call it Uint. There are way too many U's in fluid mechanics. So this is internal energy. Plus V squared over 2, that's the kinetic energy, plus the potential energy, GZ. Okay, and so, and we're going to assume that rho is equal to a constant here. Okay, and you can relax that if you have to down the road fairly straightforwardly. Okay, and we're also going to assume that rho, P, and the internal energy are uniform. Okay, and this you can prove with the Navier-Stokes equations. And it turns out this actually doesn't matter because we're not actually going to be using the internal energy for too long. Okay, but for the purposes of analysis, I'm just going to assume that the internal energy is uniform. Okay, so the integral. So I'm just going to work with this term here, and I'm just gonna work with a generic integral over one portion of the flow area. So the integral over the area of Uint plus 1/2 V squared plus GZ plus P over rho times rho V dot n hat dA. Well, I'm going to stick in this here. Oops, I'm not going to stick that in. I already did that. And now I'm just going to break this integral into the individual pieces. So you have the integral over the area of Uint rho V dot n hat dA plus the integral over the area of V squared over 2 rho V dot n hat dA plus the integral over an area of GZ rho V dot n hat dA plus the area integral of P over rho V dot n hat dA. Okay. And so now we will just work with these. And so we're assuming that Uint is uniform, so you can yank that out. But you cannot yank out rho V dot n hat dA because the V is not uniform. Okay? And this term here, there's essentially nothing we can do with this term except for maybe pull out rho, because rho equals a constant. Here we will assume that that the change in Z across a given flow area is small, so assume that's uniform. You would need a truly gargantuanly sized pipe where you would need to account for the change of elevation across a tube. And maybe if you work with sewer systems, you might have to worry about that. But sewer systems are not pipe flow problems because sewers are partially full. They are almost never fully full. Okay, and these pressures cancel out here, and you can yank that out because that's also uniform. Okay. And before I go too much further, you can see after we pull these out, we have the integral of rho V dot n hat dA. We have an integral of rho V dot n hat dA here, and an integral of V dot n hat over there. So I'll just do that integral. So note the integral over the area of rho v dot n hat dA equals, you can yank out rho because rho is constant, equals rho times times the integral over the area of v dot n hat dA, and that equals, this is by definition the volumetric flow rate, so that equals rho q, and rho q by definition is just the mass flow rate m dot. So this equals m dot if v dot n hat is greater than 0, or this equals minus rho q equals minus m dot if v dot n hat is less than 0. Okay? And so even though the velocity is non-uniform, we can just use the definition of volumetric flow rate and mass flow rate to turn them into quantities that we've been working with for a very long time. Okay? So then, u int times the integral over the area of rho v dot n hat dA equals, this here is just m dot, and I will call this plus minus m dot times the internal energy. Okay? Or this equals plus minus rho q times the internal energy. Okay? And the plus is if v dot n hat is greater than 0, and minus if v dot n hat is less than 0. Okay? And so that's basically what that integral turns into. And then the same thing for gz. Gz, the integral over the area of rho v dot n hat dA equals plus minus m dot gz equals plus minus rho q gz. Okay? And whether you use the m dot version or the rho q version is just dependent on personal preference and convenience. Okay, and now for the pressure, we have P times the integral over the area of v dot n hat dA. Well, that equals plus minus P times the volumetric flow rate, because this integral here is just the volumetric flow rate, and that equals plus minus m dot over rho times the pressure. Okay, so we know we have most of these integrals now. So we've done this integral, and this integral. Now we just got the kinetic energy term left. So that, unfortunately, we can't do too much with. And so we actually need to stick in the velocity profile and integrate it. Okay, and so the integral now for Ke. The integral over the area of v squared over 2 rho v dot n hat dA. I can move the 1/2 over and the rho out because those are uniform. So, but there's a velocity profile here, and I can't assume that that's constant. I need to basically stick that in. So we have the edge of our control volume here, and we have some u of r, and v of r equals u of r I hat. Okay, and so that would be x. Okay, and so again, we proved that through the Navier-Stokes equations that the velocity is moving only in the x direction, even in the turbulent flow regime. V bar r equals u bar r I hat turbulent. So, oops, sorry about that. I bumped the little up arrow. So even in a turbulent flow, the mean velocity is going only in the x direction. Okay? And so we know that v of r equals u of r I hat, n hat equals, we'll just say plus minus I hat, depending on which face we are thinking about. And so v dot n hat equals plus minus u. Okay? Then v squared is simply equal to v dot v equals u I hat dot u I hat, and that just equals u squared. Okay? So now, then now we know the pieces. We can actually start sticking v dot n hat and v dot v into this integral here. So we have rho over 2 equals 1/2 rho times the integral over the area of v dot v. Well, that's just u squared times v dot n hat, and that's just another u, times dA. Okay, and I'm going to move the plus minus here out to there. So this equals, implies that the kinetic energy at a section of the pipe is equal to plus minus, or the kinetic energy flux is equal to plus minus 1/2 times the density times the integral over the area of u cubed dA. Okay, and now we are integrating a pipe, and the flow is axisymmetric. So our dA are just these little rings here, like we've always had. So dA equals 2 pi r dr. So this equals plus minus rho over 2 times the integral of 0 to r times 2 pi u cubed r dr. Okay, and so that's what the kinetic energy flux is equal to. Okay, as it flows through a given, or the kinetic energy flow rate is as it passes through a section of the pipe. And so now we need to evaluate this integral, and so now we need to actually assume whether the flow is laminar or turbulent so that we know what to stick in for u. So for laminar flow, u of r equals u max, which is just the velocity at the center line, times 1 minus small r over cap r squared. Okay, and so I'm just going to take this and substitute it in. So for laminar flow, the KE, and I'm just going to drop the plus minus business here, the KE lam equals rho over 2 times the integral of 0 to r times u max cubed times 1 minus r over r cap r squared, that whole quantity cubed, times 2 pi r dr. Okay, and so I'm going to, this is a straightforward integral, it's just a polynomial, and so you do the integration, and this will equal to u average squared, and u max, equals 2 times u averaged. Okay, and if you substitute in for u averaged and do the integral, it's a straightforward integral. You'll get u averaged squared times rho times u averaged times pi r squared. Okay, well, this here is the area, and area times the average velocity is just q, and area times the average velocity, I don't know why this notability starts making geometric shapes sometimes. Area times the average velocity times density it did it again. This is just m dot. Okay, and so this equals m dot times u averaged squared, or u averaged squared times rho q. Okay, and that equals Ke laminar flow. And again, all I did was I just did this integral here and then substituted in our result that the maximum velocity is equal to the average twice of the average velocity. And just did the integral and just recognized that basically rho times u times pi r squared is just the mass flow rate going through the pipe by definition. Okay? So this definition of the kinetic energy is kind of cumbersome to deal with, and it would be much easier if we could relate the actual kinetic energy defined here to a kinetic energy based on the average velocity. So let's look at Ke based on average velocity. Okay, and I'll call that Ke averaged. Okay, and that will equal to the integral over the area of u averaged squared over 2 times rho v dot n hat dA. Okay. Well, u averaged is constant over the entire face, so you can yank that out. And what this winds up turning into, this equals 1/2 times the average velocity squared times rho times u averaged times pi r squared. Okay, because and this is just basically almost everything is constant here, and you're just left with an integral of v dot n hat dA, which is just q. Okay, and so this equals 1/2, and you'll recognize this as m dot as 1/2 u averaged squared times m dot, or equals u averaged squared over 2 times rho q. Okay, and so this that Ke based on the average velocity is just equal to this. So basically, you just take half of the average velocity squared and multiply it by the mass flow rate, or multiply it by density times the volumetric flow rate. Both work. And so, but you can see by comparing the kinetic energy based on the average velocity and the kinetic energy based on the true integration of the profile, you can see that they're actually quite a bit different. But this formula here is just a lot easier to work with, because u average equals q over a. And so you typically know the volumetric flow rate. So basically this piece here is known fairly well, and you know the area. And so this formula here is a lot easier to use than actually sticking in the integrals and things like that. So how do we use the simplicity of this formula here but retain the accuracy of doing the actual integral? Well, we define, so it is easier to work with Ke averaged. Okay, but we need to correct it, and so we'll define an alpha, and that's just a bogey factor. And alpha is defined as Ke from the actual velocity profile over Ke of the averaged. Okay, and so that implies that the actual kinetic energy equals this bogey factor times the kinetic energy based on the averaged velocity. Okay, and so for laminar flow, alpha lam equals Ke of the laminar flow over Ke based on the average velocity, and we just stick in our results. This equals U averaged squared times m dot over U averaged squared over 2 times m dot. Almost everything cancels out, and this equals 2, equals alpha lam. Okay, so the bogey factor for a laminar flow is a factor of 2. So that is, if you just base the kinetic energy solely on the mean velocity at a given cross-section, your kinetic energy is off by a factor of 2 for a laminar flow. Okay, and so what about turbulent flow? Which is the more practical case anyhow. Recall for here, we'll just use U bar, which is just the mean turbulent velocity, equals U max times 1 minus r over cap r to the 1 over n. Okay, and here we need to calculate the average velocity. U averaged is defined to be 1 over a times the volumetric flow rate, v dot n hat dA. And if you stick this into here and do the integral, I'm not going to do it. This equals U max times n squared over 1 plus 3n plus 2n squared. Okay. Then alpha for the turbulent flow, or the bogey factor for is kinetic energy of the actual turbulent profile over kinetic energy based on the averaged velocity. And so this equals the integral 0 to r times 1/2 rho U max cubed times 1 minus small r over cap r to the 3 over n times 2 pi r dr. Here I just basically used the generic kinetic energy formula that we derived with the integral and just stuck in this velocity profile. And I'm going to divide that by the kinetic energy based on the averaged velocity, that's integral 0 to r, times 1/2 rho times U averaged squared, times U averaged cubed, sorry, times 2 pi r dr. Again, these is just a calculus 2 exercise at this point, mainly for this top integral here, and this bottom integral, we actually already did that, and that integral is actually right here. And so, but if you do the math and go through everything and don't make a mistake like I did a couple of times, this equals 1 plus 3n plus 2n squared, that whole quantity cubed, over 4n to the 4th over 9 plus 9n plus 2n squared. Okay, and so we can make a little table here for n, 4, 5, 6, 7, 8, 9, 10, and alpha turb. Okay, and so this is the correction factor. If n is 4, it's 1.156. If 5, it's 1.106. For 6, it's 1.077. For 7, it's 1.058. For 8, it's 1.046. For 9, it's 1.037. and for 10 it's 1.03. And so note that these are all close to 1. Okay, and so these are all close to 1, so you can assume that if the flow is turbulent, alpha turb is approximately 1. Okay, and the reason that that alpha turb is approximately close to 1, and you can use that for calculations, just has to do with the velocity profile itself. So in our pipe flow, for the turbulence, the mean velocity profile looks something like this. Okay, and so it's very flat, and because it's very flat, the deviation from the average velocity profile would look something like this. And so it's actually not that much different. So the mean velocity profile for a turbulent profile is not that much different than the average velocity profile. Okay? And so it's very flat, and because it's very flat, it's not that much different. The actual mean velocity profile U bar, which is right here, is not that much different than the average velocity profile in red. Okay? Which is perfectly constant. And so we did all this work just to prove or show that our bogey correction factor for turbulent flow, which is the more practical case, is just simply 1. Okay? And so now finally we can go back to our problem, and that the kinetic energy integral, which is what we were working with, equals 1 over 2 times rho, the integral over the area of v squared, rho v dot n hat dA, that equals alpha ke based on the average velocity profile. And so that equals alpha times u averaged squared over 2 times m dot. And of course there's a plus minus out here too. Okay, and so our nasty kinetic energy integral is just in terms of numbers that we know. It's just you now have to pick an alpha based on the flow. And now if we really wanted to be anal, we could probably choose a 1/7 profile and use an alpha of 1.058. But the thing is, the n of being 7 is, you don't know what n is. You just know that it's going to be somewhere between 6 and 8, something like that. And so you can say those are very close to 1. Certainly within the estimate of the loss coefficients and everything else, a shift of 1% or 2 on alpha isn't going to make or break your calculation. Okay? So now we know all the pieces to do the integral. So then, back to the control volume. And with that, we had the integral over the control volume of E plus P over rho V dot n hat dA is equal to W dot in minus W dot out minus Q dot loss. Okay, and the integral, and I'll just draw a quick little cartoon of it. A very badly drawn cartoon. And we assume that the flow is going in. Okay, and so now we just do this control volume here where we're analyzing the flow going in and out of the pipes. And what we wind up with is we now know how to do this integral over area 1 and area 2, so we just stick them in. And so the integral over area 1 of the internal energy plus the kinetic energy plus the potential energy plus the flow work, P over rho, rho v dot n hat dA1, because this here is what E is. Oops, did that a little bit too far. Okay, and where U int is the internal energy. Again, there are way too many U's and V's in fluid mechanics. And this equals, because we are on the left face, V dot n hat will be less than 0. So we choose the minus sign. This will be minus the internal energy on face 1 times m dot 1 plus alpha 1, m dot 1 over 2, U averaged squared at state 1, plus m dot 1 gz1 plus p1 over rho m dot 1. Okay. So then the integral over area 2, which is the outlet, the integral over A2 of E plus P over rho V dot n hat dA, that will equal to the same thing. Oops, need the scissors. That will equal to the same thing. But V dot n hat is greater than 0, so it's plus instead of minus, and it's at face 2 rather than face 1. Okay. Then, I'm not going to prove this, but from conservation of mass, m dot 1 equals m dot 2 equals m dot. And if rho is equal to constant, if rho is equal to constant, the volumetric flow rate going in is equal to the volumetric flow rate going out is equal to just the volumetric flow rate, and rho 1 equals rho 2 equals rho, and I've been using that one all along. Okay. Then, using this, the integral over A1, E plus P over rho V dot n hat dA1, plus the integral over area 2, E plus P over rho V dot n hat dA2, that will equal to, I'm just going to take this result here and add it to this result here, and just noting that m dot 1 and m dot 2 are just m dot. And then I'm just going to factor everything out. Okay, and so this will equal m dot times uint 2 minus uint 1 plus 1/2 times alpha 2 times U average squared over 2 minus alpha 1 times U averaged, the average velocity at state 1 squared, plus G Z2 minus Z1 plus P2 over rho minus P1 over rho. Okay, and so that's what the and this equals the surface integral of the entire surface integral of E plus P over rho times rho V dot n hat dA. Okay, so now back to the full problem. Okay, where we had the surface integral of E plus P over rho V dot n hat dA equals W dot in minus W dot out, and I'll call this W dot P because W dot in because the power in will typically come from a turbine, and I'll call this W dot T. I mean the work in will come from a pump, and the work out will typically come from a turbine, so I'll call that W dot T, and minus a heat loss term. Okay. And so we already have this piece here, and that comes from, so this term here is integral, is actually this integral here, because we're assuming there's no flow, that the walls of the pipe are impermeable. So we have m dot times u int at state 2 plus alpha at state 2 over 2 times u averaged squared at state 2 plus gz2 plus p2 over rho minus m dot times u int at state 1 plus alpha 1 over 2 u averaged at state 1 squared plus gz1 plus p1 over rho. And that is equal to the power input from a pump minus the output for any turbines minus the heat loss. Okay. Or I'm going to do some light rearranging here. We have P2 over rho plus alpha 2 u averaged at state 2 squared over 2 plus gz2 minus the same thing for state 1, p1 over rho plus alpha 1 u averaged 1 squared over 2 plus gz1 is equal to W dot from the pump divided by m dot minus W dot out, or W dot out for any turbines divided by m dot minus, or I'll say plus, the heat loss term over m dot plus the internal energy at state 1 minus the internal energy at state 2. Okay, and this entire term here is called the head loss. Okay, and this is sometimes called head. Okay. So then I'm going to work with that, and I'm going to divide by G. We have P2 over rho G plus alpha 2 U averaged squared over 2G plus Z2 minus P1 over rho G plus alpha 1 times U averaged at state 1 squared over 2G plus Z1 equals the head loss divided by G plus W dot in over G minus, pump, any work input due to pumps or other things, minus W dot out over G. Okay, and this should have a negative sign here. Okay, and I'm going to call this HL over G as cap HL T, and this is called the head loss. Okay, and it has units of length. Okay. So then finally, and we have P over gamma plus alpha U averaged squared over 2G plus Z, and that's at the outlet of our control volume. I don't like labeling them 1 and 2 if you don't have to. Plus P over gamma plus alpha U averaged squared over 2G plus Z at the inlet of the pipe is equal to minus the head loss plus the pump work in over M dot, I forgot M dot's over here, M dot G minus the work out due to turbines, M dot G. Okay, and so this equation is based on conservation of energy, and you can use this to account for viscous losses in pipes. And so where the viscous losses comes in is actually this head loss term, and this actually represents your losses. And so physically, what this head loss term represents, if I go up to where we defined it, which the head loss term is just based on the heat loss from the pipe times the change in internal energy. Okay, and so essentially physically what's going on is if we draw the pipe and the velocity profile, there is some there is actually a friction between the layers of fluid as they slide over one another, and just like if you take friction from, say, rubbing your hands together, the heat builds up, and so all the power that you're putting in rubbing your hands is actually going into heating your hands, and that goes into, if you draw the control volume around your hand, there is a heat loss because your hand is losing heat to the outside, to the air above it, and also the temperature of your skin on your hands also changes. But it's not like you can apply heat to your hand and your hands suddenly start moving. And so it's the same thing for the fluid. And so what these viscous losses do is they cause a combination of heat loss to the pipe or a slight change in the temperature. If you remember the example I did in class where we had that water flowing downhill from a very long reservoir, is that all those losses, and it was 20-30 horsepower, amounted to a 0.01 degree change in temperature. And so it was essentially nothing, immeasurably small, but in terms of actual performance numbers, these terms are huge. But just remember that the pressure drop due to viscous effects from the wall, or minor losses from the components of the pipe, are basically, the second law of thermodynamics says that those are irreversible losses that convert kinetic energy into heat, and there's no reversing that. So now, to tie everything together, so we just need to figure out how to calculate this term here. So how do we calculate the head loss? Okay, well, as I said, it comes from viscous effects. And is irreversible. And it is delta P divided by gamma due to friction. Oh, and I forgot, recall that gamma is just equal to rho times g, the specific weight. Okay? So then the head loss, which has units of feet or meters, is equal to the sum of all the pressure drops for the major losses, plus the sum of all the pressure drops divided by rho g for the minor losses. Okay, and then note that delta P over rho g for the major losses is equal to the Darcy friction factor times L over D times rho u averaged squared over 2 times 1 over rho g, and this equals F L over D times u averaged squared over 2g. Okay, and so those are the major flow losses, and the Darcy friction factor F lam equals 64 over RED, and F turbulent equals a Colbrook equation or Moody chart. And it is turbulent if RED is greater than 2300. And also, I'll just make a note here that the kinetic energy correction factor is approximately 1, and alpha of the laminar is equal to 2. Okay? And so now we know how to compute the head loss due to major pipe losses. And the reason up here that I have a sum is I could have a pipe system, I'll just sketch one down here, that looks something like, I don't know why it does that, that looks something like this. Okay, where we have a section of pipe, here that is very long, a section of pipe here, a section of pipe here, and a section of pipe here. And so we would have to add up the delta P for this section here, this section here, this section here, and this section here, and those would all represent major losses. So we basically just need to add them all up. And now for the minor losses, delta P over rho g minor equals the loss coefficient for a particular component times rho u averaged squared over 2 times 1 over rho g, and that equals the loss coefficient times the average velocity squared over 2g. Okay? So the head loss is equal to the sum of all the major losses U average squared over 2G plus the sum of all the minor losses. So that's the sum of the loss coefficient times U average squared over 2G. Okay, and this is minor. And this is major losses. Okay, and so now I'm going to wrap it up, but I'm going to go over one last thing, and that's what do you do if you have a non-circular duct? Well, that's because, like, say for your HVAC system in your house, the ducts tend to be rectangular in shape. And then you have a little vent sticking off to the side of it. And that ductwork is quite often rectangular. So how do we handle that? Well, to first order, essentially what you can do is you can use what's called the hydraulic diameter. So use hydraulic diameter DH. Okay, and the hydraulic diameter DH equals 4 times the wetted perimeter over the, 4 times the area over the wetted perimeter. Okay. And so what you do with this hydraulic diameter then is you then use F based on RE DH equals a rho U averaged times the hydraulic diameter over the viscosity. And so to first order, as a first order approximation, you use the formulas for a circular duct, the same turbulence transition criterion, but instead of using the diameter of the pipe, you use a hydraulic diameter. And so, for example, if we consider a rectangle of height A and width B, DH equals 4A over the perimeter. So that equals 4 times AB over the perimeter. So you have 2. You have a B here and a B here, so those add together. And you have an A here and an A here. So that's 2. That's 2A plus B. Okay, and so that's equals 2AB over A plus B. Okay, and so if A is equal to B, if you have a square, it's just equal for a square. A equals B implies that DH, if you stuff in A is equal to B into this expression here, DH is just equal to A. And as a sanity check, we can compute DH for a circle. and we better get D. So dH equals 4A over the perimeter. Well, that equals 4 times pi r squared. Or I'll do this in terms of diameter. 4 times pi over 4 d squared, that's the area, times the perimeter. Well, that's just a circle of diameter d. So that's just pi d. Equals d. And so essentially, if you have a non-circular duct as a first order approximation, you can base the friction factor and everything, use the formulas for a circular duct, but base the diameter that you use in the Reynolds number, base the diameter off of the hydraulic diameter. And so that wraps up the theory for Chapter 8, and now the next lectures I'm going to go over a bunch of examples.